Today I would like to share with you a new approach and some new results I just got some days ago, and I would like to receive some feedback from you if possible. So basically I went for analysis of TMS-induced oscillations modulated by some glutamatergic drugs as perampanel, dextromethorphan, and nimodipine. Basically, perampanel is an AMPA receptor antagonist, dextromethorphan an MDA receptor antagonist. These are the two main carriers. And then we use nimodipine, which has a completely different mechanism. It blocks the voltage-gated calcium channel. And then, of course, we had a placebo as well. So the study design is, so to say, a typical study design for studying drug effects. We measured the resting motor threshold before drug assumption. We had 3 minutes of resting state EEG, eyes open and eyes closed. And then a session of TMS EEG, drug assumption in 2 different times, and then again the same paradigm repeated after drug for studying the drug effects. We studied TAPS. We had some results which were to some extent complementary to the results we obtained with TAPS on GABAergic modulators. And we wanted to go further analyzing TMS-induced oscillation power. Therefore, we considered a technique we developed in 2017, which is mainly given the single trials inclusive the evoked response, we subtract the average evoked response from the single trials, and we Fourier transform the single trials without evoked response to study how the oscillation power changes due to drug assumption. In this case, for glutamatergic drugs, we considered 4 windows in the time frequency space, 400 milliseconds after TMS pulse. Basically an early alpha and an early beta, and a late alpha and a late beta, with the topologies associated, which are shown here in this figure. However, when studying the effects of perampanel, dextromethorphan, and nimodipine on the oscillation power pre and post, we didn't find any significant results, despite of the fact that at least post versus pre for late alpha and late beta in perampanel show quite different topographies, quite different EEG topographies. But the cluster statistics we applied as from the paper of Maris, Schoffelen, and Fries didn't produce any significant result. This was a little bit weird, and we had other studies with negative results. So this approach could be potentially not too sensitive to changes. We are probably underestimating the changes in the oscillation power, and this was rather evident. At least some kind of indirect evidence was provided by the results of resting state oscillations pre and post drug assumption. So the power for perampanel was extremely increased to the level that the cluster statistics became rather uninformative, especially because the increase in oscillation power was pretty strong and generalized, both in the topographies and in the frequency bands. We had some results for resting state for nimodipine and in the gamma band for dextromethorphan as well. But still, I had some, so to say, I had some problems in wrapping up the results because this prominent effect in resting state was to some extent in contrast with the absence of results for TMS-induced oscillations. Therefore, I tried a new and to some extent more sophisticated approach, which is a general approach. It's a way of decomposing and a way for a parsimonious use of high dimensionality data. The idea is the following. If we have a 3D space, basically a 3D space like a 2D space can be decomposed in a linear combination, in a sum of the outer products of different tensors. Basically, the parafact tensor decomposition is an n-dimensional PCA. But for some constraints I won't delve into, the PCA is always defined for everything but a rotation. So we generally use a rotation to explain, to maximize the explained variance, so that the algorithms are relatively deterministic. But one rotation is free, whereas the parafact result is well defined and unique. So basically, if we apply this general technique to our case in a single subject, we have a 3D space which is defined by the EG channels, frequency and time. For each time we can produce, for each trial we can produce a time frequency plot of power. And the idea is that by means of a limited number of components, this 3D space can be decomposed in some in this case they're called tensor components. Each of them has a special dimension, which is the channel topography, a frequency spectrum, and a time course of its own. So each tensor component provides for a frequency and a time plot on the other dimensions. This was first published on Scientific Report by this guy whose name is very difficult to pronounce, Tangiri-Yasakul. If we add two more dimensions, as in our case, with the number of subjects, 4th dimensions, and number of conditions, we had basically 8 dimensions. So the 4 post-drug and the 4 pre-drug conditions, we end up with a 5D space, and we search for the so-called master components, which are components in this 5-dimensional space and common to all dimensions. So what I did, basically, it's a new analysis on the frequency range of 430 Hz and on the time 30 to 400 milliseconds after the TMS pulse. And I found 4 main components. One characteristic of the tensor decomposition is that the number of components is chosen a priori. How I arrived to the 4 number in the previous paper, they report, and I experienced it myself, that with 4 components, one reaches a plateau in the explained variance of the data. And moreover, the 4 components in my case were topographically, spatially and temporally different. I will show you later. Whereas with 5 components, I started to have some redundancy, and with 3 some instability. So I'm rather confident that 4 components is the right choice, is the right compromise. For each component had a frequency spectrum, a time course, power distributed over channels, an effect over our 16 subjects, and more important, an effect for each state. This is pre-perampanel, this is post-perampanel, and it's already evident that something is happening on the tensor components, whereas very little happens for dextrometer, nimodipine, and trust me, for placebo. I applied statistics, especially conceived for this approach. Basically, it's a permutation analysis to test the different pre versus post drug. So the aforementioned 4 components are considered the master components, the components to refer to. Then the 5 tensor, the 5 tensor object encompassing our data is permuted for 1,000 iterations. Each iteration generates 1 folder with the shuffled components. The shuffling happens on the 4th and 5th dimensions. So that means subjects and conditions. With each iteration, a new set of tensors is generated. And I will show you results with a first absolute test to check where our master component places with respect to this distribution of shuffled sensors. Then I will subtract the value on the 5th dimension, post minus pre drug, and show some other statistical results with the second test, where the master is basically post minus pre. We chose as a level of chance that the master is significant if its value is larger than the 70.5% or smaller than the 2.5% of the distribution in the histogram. And these are the results. The strength of each shuffled information is shown in the histograms, and the green dot is where our master component places. Then the dimension is 5. These are results for the tensor component number 1. This is for the tensor number 2, number 3, number 4. What is reassuring is that for the pre-drug, the master component always falls within the realms within the borders of non-significance. And same for placebo, pre and post, all of the 4 components. And this is already a good sanity check. Then for the second and the third component, for post perampanel assumption, we find a significant increase in the strength of our respectively second and third component. And this is the absolute result, which provides for some sanity checks. Then, if we subtract post minus pre, we have basically only one histogram for each drug and each tensor component, and we find the same significances for a perampanel for component number 2 and number 3, basically the red and the yellow one. And they are increasing. So there are increases in the strength of such components due to perampanel. Of course, in this second test, one could reach significance even if the absolute values are of pre and post are both non-significant. But in our case, the post was already absolutely significant, and the difference is also significant, showing an increase of the 2 components, which were showing a rather broad frequency spectrum. And this is, to some extent, relieving for me, because basically factorizing the components and being able to focus on the effects of the second and third component, which have a strength which is relevantly smaller than the component number 1, I'm able to see some results due to perampanel assumption, which were not detected by the original analysis on oscillation power. So basically, next natural steps would be step analysis with the same approach. In the near future, I want to try a source localization of the components to analyze better the neurophysiological meaning and relevance of them. And then if the analysis reveals itself robust enough, I would be interested in the use of such approach for the analysis of single subject data, even in the context of connect to brain.